welcome to our video here on the integral test and the P-series. So far we only know a couple tests for testing out series. So we're going to go ahead a couple more here today. So integral test is a test where if f is positive, continuous, and decreasing, if these three things happen, and then you'll be good to go ahead and use the integral test. Then the series and the integral both either converge or diverge. All right, so we're going to focus on that part. I'll do the error here in just a second. So we're going to go ahead and go to this guy over here. So again, this is what it's saying is if we can prove that f is positive, continuous, and decreasing, then this series will either converge or diverge based on if the integral from 1 to infinity converges or diverges. All right, and this is good for when x is greater than or equal to 1. All right, so let's go ahead and do this first one right here. So first off, you got to figure out if this is positive the entire time. And if you ever don't know that, you can just go off to the side and just write down what the first couple of terms are. And it's not a big deal. So for this guy right here, if I have 1, I'm going to have 1/2. And then at 2, I'm going to have, looks like 2/5. If I have 3, it looks like I'm going to have 3/10. Okay, so that's kind of enough assuming that same pattern. So as you can tell, this is positive the entire time. All right, and there's no reason it'll ever get negative anyhow, because you get larger and larger and larger. This is continuous. Again, we're just looking from 1 to infinity, and yes, this is continuous. There's actually no discontinuity here at all. And is it decreasing? So we start at 1/2, which is like 0.5, and then 2/5, which is 0.4, and then 0.3. So yeah, it's decreasing. So we have to state that f is positive, continuous, and decreasing. You have to say those three things here. So f is positive, continuous, and decreasing. And then we can go ahead and find the integral of this. So we're going to find the integral from 1 to infinity of this. I'm going to change the n's to x's. It's not a big deal. Okay. So I just need to find this. Now the actual value itself I don't really care about, but I do care if I get a number, if I do not get a number. So we're going to do the limit as b approaches infinity from 1 to b of this x over x squared plus 1 dx. So we would go through and find this. This would just be a u sub. If you don't mind, I'm going to kind of skip the integration step because that's not the part I'm too worried about. You can integrate this by doing u sub. You're going to end up getting here a 1/2 ln of x squared plus 1, and that's going to go from 1 to b. So what's that going to tell me when I plug my b value in? That I'm going to get limit as b approaches infinity of 1/2 of ln of b squared plus 1 minus 1/2 ln of 1 squared plus 1. All right, so if you plug an infinity into this ln, so ln's increasing. So if you're going on forever and ever, it's actually always increasing. So this is actually going to equal infinity. So this diverges. I can't spell diverges apparently. So this one diverges. So this is going to, so therefore the series diverges by the integral test. Okay, and so there's that one. Go ahead and go to B here and find this problem. I'll do this in different colors so that we're not overlapping too much. So again, we're learning about the integral test. So obviously, we're going to use the integral test. But if I were to use one of my previous tests that I learned before, this one cannot be broken up into partial fractions, so it's not going to be telescoping. This is not geometric. And then if I were to find the limit out to infinity of this, I would get 0, so it would be inconclusive for the nth term test. So the fourth test I'm learning here is the integral test, and that's why you have to apply it here, because the other 3 tests that I know do not work. Okay, so for this one, looks like here it's going to be positive. As the numbers get larger, we're going to be decreasing, and this is continuous all the way through. So we can say that f is positive, continuous, and decreasing. You have to state that. You don't state that, the integral test is going to fail. You're going to lose points on that one because you need to state why you're able to use the integral test. Okay, so let's go ahead and find the integral from 1 to infinity of this guy. Oops, sorry, I use x's. X squared plus 1 dx. So I'm going to find the limit as b approaches infinity. From 1 to b of 1 over x squared plus 1 dx. This is actually an arctan. So we're going to do the limit as b approaches infinity of arctan x from 1 to b. So hopefully you know what arctan looks like, or you remember what it looks like. We've talked about it previously. So plug in the b and the 1. So arctan, in case you forgot, looks kind of sort of like this. Okay, so it's got two asymptotes, two horizontal asymptotes here, and it's going to be at pi over 2 and negative pi over 2. So as we go out to infinity, we're going to get closer and closer to pi over 2. Arctan of 1 is just going to be pi over 4. So this is going to equal an answer of pi over 2, so this converges. Pi over 2 doesn't really represent much for the integral test other than, yeah, the series is going to converge. All right, so here we're going to say that the series converges by integral test. Okay, so it's very important here that, oh, by the way, this should be, I don't know how I did this really bad math. This should be pi over 4. This is not the sum. That's important to note, that that's not the sum whatsoever. So integral test is not going to help me find the exact sum. It just tells me if it's going to converge or not. So you did an example where it diverges, one where it converges. So now there's a last little part of my little theorem up here that I just didn't talk about. So if the series converges to S, then the remainder right here, which is the series minus the number of terms in the series, is bounded by 0 to whatever the integral happens to be. So here we're just talking about error, okay? So you can kind of estimate what the sum is based on the remainder, okay? So what does this look like in a problem? I'll show you right here. So approximate the sum of the convergent series. So this is nice. It tells us it converges. So that's going to match up right here because it says the series converges. So this tells us this converges using this first 6 terms. So what we have to do is, well, find the first 6 terms. So 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th plus 1 over 4 to the 4th plus 1 over 5 to the 4th plus 1 over 6 to the 4th. Okay, so this is going to give me a value of, if you just go ahead and type this into your calculator, give me a number of 1.0811. Okay, so this is the first 6 terms. Okay, so our actual sum will be kind of sort of close to that because if you notice, as we keep adding numbers further and further out, not much is going to change here, just like the maybe the 10th place might change, the 100th place will change, the 1000th place will change based on how far out we go. So what we're going to do here is we're going to integrate from whatever number term we're at to infinity. Okay, so for this one, we're going to integrate from 6, because we did 6 terms, out to infinity of this 1 over n to the 4th. And then whatever value this gives us is going to end up being my maximum error here. Okay, so when I go ahead and do this, I'm going to get the limit. B approaches infinity. 1 over b, sorry, 1 to b, x to the 4th dx. I'm just going to go ahead and just tell you what the answer is. I'm just trying to save a little bit of time here. You're going to get 1 over 648. And I'll try to put this in perspective for the problem. So this is approximately 0.0015. Okay, so what this is saying here is that my error that I have here out to 6 terms is 1 over 648. So at the most, this series can be 0.01811. It totally could be. It's not, because we're going to keep adding more and more terms. But at most, it's going to have a it's going to go up to 0.0015. Okay, so at most, this could be 1.0826. That's the most that it could be. So somewhere in between here, and then if you add that number, is going to be what the series converges to. Okay. So now let's talk about the P series. So the P series is related to the integral test here. So it says the P series of the form n to the P, 1 over n to the P, which looks like this right here, is the P series. So it's really when, just talk about the power, P series, power. And this is only when P is positive. So if P is 1, then we get this value right here. So this is what the P series test is. So this is going to converge if P is greater than 1. It's going to diverge if P is less than 1. Or it's going to diverge if P equals 1, and this is known as the harmonic series. All right, and that's actually that right there is when you do 1 plus 1/2 plus 1/3. It actually does not. That actually diverges here. So that should make sense, because if we have a really, really large power, we're going to get closer and closer to 0 very quickly. So this is just saying use the integral test to try to figure out what values would cause 1 over n to the P converge. And for all of these situations, F is going to be positive, continuous, and decreasing. So I'm not going to write that out for each one, but I'm going to do just a quick little integral test just to prove this. So when P is 1, when P is 2, and when P is 1/2. Okay, so it's all I'm doing right now. I'm just proving the P series. So when P is 1, I'm going to get 1 over infinity of n equals 1 of 1 over n. Okay, so this is going to be the limit as b approaches infinity. Sorry, ignore that. From 1 to b of 1 over x dx. For that value, I'm going to end up getting the limit as b approaches infinity. I am going through this really, really fast, just because I want to show you every little step of the way here. Integral 1 over x dx is just ln of x, so I'm getting ln of b minus ln of 1. Ln of b is increasing the entire time, so if I go out to infinity, it's always increasing, so this is going to be infinity. So this diverges. So when p is equal to 1, we diverge. What about when p is equal to 2? So we're going to do the same thing. So this is, I don't want to get too far ahead of myself. This is for 1 over n squared. So as we go to infinity, 1 over b, 1 over x squared dx. Antiderivative here is going to be negative 1 over x. So again, kind of jumping ahead just a little bit here. I'm going to get, just checking all my work here, negative 1 over x from 1 to b. And this is going to give me limit as b approaches infinity, negative 1 over b minus negative 1 over 1, which is going to give me, if I go to infinity here, I'm actually going to get a value of 1. So this converges. So this one will converge by the integral test. And again, I'm not doing anything too formal here. I'm just trying to show you that, hey, this works for the P series in this situation. When P is 1, when P is 2, it converges. So P is 1/2. That should diverge because that follows B. So if I just go through this, all right, so if I do the limit as b approaches infinity of 1 to b, 1 over x to the 1/2 dx, what is this going to give me here? This is going to give me, 2x to the, so it's going to give me 2 root x evaluate that from 1 to b, and then hopefully kind of see from here that root x is always increasing. So if I go out to infinity, it's not going to change anything. It's actually going to equal infinity, so this is why this diverges. Okay, so these 3 examples were just me proving. So this is part C, part A, and then part B from up here. I'm just trying to prove to you that the p-series does work this way. So you don't need to show this work every single time for a p-series. So for this one right here, I would just rewrite this as n approaches 1, n equals 1, goes out to infinity. This is really n to the 3/2, okay? Because it's n times root n. So this is going to converge because p is equal to 3/2. So this is the work you need to show. So this converges by p-series test. All right. And again, that works because that is larger than 1. This is the work you need to show. Make sure you do show, I almost forgot that. Make sure you do show that this is greater than 1. I know it's very, very silly, but you have to show that you know what you're talking about. You can't just be like, oh, p's 3/2. Oh, I forgot what to do. I'll just do a 50-50. So you actually need to say that, yeah, it's greater than 1, and therefore it converges by the p-series test. And that's going to wrap up our video here.